Hello everyone, this is Xuhai. The paper I'm going to present today is EarBuddy, enabling on-face interaction via wireless earbuds. On-body interaction refers to the use of the human body as an input or output channel. It can help expand users' input bandwidth, provide convenient input techniques, increase interaction efficiency, and therefore improve user experience. A wide range of human body parts have been leveraged for on-body interaction. Here are some examples. Xuhai et al. Proposed to leverage biting as a novel interface that allows users to input with different levels of biting force, positions, and frequencies. Harrison et al. Used a ceiling-mounted infrared camera to locate a person's arms and hands and the digital light processing projector to shine the interface onto the user's limbs. Zhang et al. Identified hand posture using an ultrasonic speaker on the thumb and receivers placed at the thumb and the wrist. Fukaori et al. Added pressure sensors on a pair of socks to enable users to input foot gesture by applying pressure with different parts of the foot. However, these techniques require additional hardware, such as pressure sensors, cameras, and ultrasonic speakers. As shown in these examples, these customized sensors limit their deployability, scalability, and generalizability. Our work takes advantage of the growing popularity of wireless earbuds as ubiquitous sensors for on-body sensing. Apple sold tens of millions of AirPods, and other companies like Samsung and Sony are also expected to show comparable trends in the uptake of their earbuds. The fact that wireless earbuds rest in a person's ears means that their microphone is conveniently situated near multiple surfaces that are suitable for on-body interaction: the cheek, the temple, and the ear. Tapping and sliding fingers across these surfaces generate audio signals that can be captured by an earbud. Based on such an observation, we propose EarBuddy, a real-time system that leverages the microphone in commercial wireless earbuds to detect tapping and a sliding gesture near the face and ears. EarBuddy can support natural, eyes-free interaction with devices in daily routine. Users can easily control a music player or react to a notification by EarBuddy. Since EarBuddy augments the capabilities of devices that are already commercially available, our technique can easily be deployed through software updates to the phone to provide new interaction experience for users. To enable this interaction technique, we start by developing a design space to generate valid gestures on the face. We propose 3 types of gestures: tap-based gesture, slide-based gestures, and complex gestures. For tap gestures, we propose 7 areas that users can single or double tap, including temple, cheek, mandible angle, mastoid, top ear rim, middle ear rim, and bottom ear rim. For slide gestures, we propose 4 areas that support simple sliding gestures. Users can slide on cheek in different directions, the same for ear rim, mandible base, and ramus. We also propose 3 complex sliding gestures on cheek: a 2-finger spreading gesture, pinch gesture, and a lasso motion. Overall, we propose a design space with 27 gestures on face and ears. To narrow down the gesture set to a subset that can be naturally performed, quickly remembered, and easily classified, we conducted a study with 16 users to identify a subset of the most preferable gestures. The study was conducted in a quiet room with an ambient noise level around 35 to 40 dB. We used a pair of Samsung Gear Icon X for data collection. Each participant performed all 27 gestures 3 times using their right hand, with counterbalanced order. After performing the gesture, the participants was asked to rate the gesture according to 3 criteria along a 7-point Likert scale: the simplicity, the social acceptability, and the fatigue. This figure shows typical example signals for all gestures. Note that in the right bottom part, gestures like sliding on the mandible and the ramus, as well as complex gesture, have a pretty low signal-to-noise ratio and are barely visible in the spectrogram. Here, we show all gestures ratings sorted by the sum of the scores. Overall, tapping gestures received higher scores than sliding gestures. We selected the best 8 gestures according to 4 criteria. The first is the signal-to-noise ratio. We removed gestures whose signal-to-noise ratio was lower than 5 dB. The second is signal similarity. we removed gestures whose similarity score, calculated by dynamic time wrapping, was among the bottom 25 percentile. We also referred to design consistency. For each single tap gesture that was eliminated, the corresponding double tap gesture was also removed, and vice versa. Finally, we ranked the remaining gestures using the user preference scores. The gesture selection procedure resulted in a gesture optimized for user preference and microphone detectability. Our final gesture set has 6 tapping gestures and 2 sliding gestures. The 6 tapping gestures include single and double tap on cheek, mastoid, and middle ear rim, and the 2 sliding gestures include top to bottom slide on ear rims and ramus. We then conducted a data collection study for the 8 gestures in both a quiet environment and a noisy environment. The noisy environment was simulated by playing office background noise at 55 dB. Overall, we collected 14,000 data samples. After annotation and filtering samples obscured by noise due to some software or hardware issues, we had about 11,000 samples for model training. We trained 2 models for EarBuddy, one for gesture detection and one for gesture classification. For gesture detection, we trained a 3-layer neural network binary classifier based on MFCC features. Together with a smoothing method, the model has an accuracy about 98%. For gesture classification, we leveraged transfer learning and used a pre-trained dense net. We fine-tuned the model using the data we collected. We further augmented our data by mixing noise, adding frequency and time masks, and flipping the audio, so that we can have a larger number of training samples. We then trained a classifier using stochastic gradient descent with momentum and cosine annealing learning schedule. Our model achieves an accuracy of 95.3%. The confusion matrix indicates how well each gesture can be recognized by EarBuddy. In addition, to investigate the feasibility of a model that could recognize gestures by new users, we trained our best model configuration using leave one user out cross-validation. Doing so produced an overall accuracy at 82%. In a real-world situation, it is realistic to ask a new user to perform each gesture a few times before using the system, such as during a tutorial. We tested this approach by saving our leave one user out model and further training it on a small number of samples of each gesture from the ignored user. The performance approaches the population test accuracy with additional samples, reaching 94% with 30 gestures. Based on the 2 models, we implemented EarBuddy that detects and recognizes gesture in real time. EarBuddy first used the gesture detection model to find the audio segments that contain the gestures by applying the gesture recognition model on the MFCC feature window. Then, for the detected sequence, the raw audio is converted into a Meyer spectrogram and fed into the gesture classification model to recognize which gesture the user performed. Finally, we conducted a user study to evaluate the usability of EarBuddy. We invited 12 participants back from the data collection study and used a within-subject factorial design to measure the speed and the user's subjective ratings of EarBuddy. 2 independent variables are the task and the setup. For the task variable, we developed 3 common applications. The first is controlling a music player. Participants control music with 5 actions: play pause, volume up, volume down, next song, and previous song. The second is answering a phone call. When the simulated call came in, participants could either answer, reject, or mute the call. The last is reading notifications. Participants consumed a notification and could either open it for more details or delete it. As for the setups, we compare EarBuddy with 2 baselines, the table setup and the pocket setup. In the pocket setup, participants need to remove the phone from the pocket and then complete the task. In the table setup, the smartphone was put on the table and they need to pick it up to interact. In the study, our system had a low segmentation error rate and a low recognition error rate. We used ANOVA of a generalized linear mix model and post-hoc z-test on the time difference. Our results show that EarBuddy significantly sped up interactions by 34% compared to the table setup and 56% compared to the pocket setup. In addition, ANOVA on a generalized linear mixed model with paired Wilcox test on the rating scores showed that EarBuddy had lower physical demand, required less effort, and had better performance. Users also provided positive feedback, saying that EarBuddy can be used easily, conveniently, and naturally. To summarize, in this work, we propose EarBuddy, a new input technique supported by wireless earbuds. We create a design space for gestures near the face and the ears and conducted a study to select an optimized gesture set. We then trained gesture recognition models and evaluated the usability of earbud study. Our work demonstrates how EarBuddy-based sensing can be used to enable novel interaction techniques, and we hope to see other researchers leveraging earbuds and other commercial wearables to support novel forms of interaction. With this, I would like to end my talk. Thank you all for your attention. I hope everyone is staying safe and healthy around the world. Bye.